Good morning, everybody. Today we're going to do a lecture on opening epoxides with strong nucleophiles. What do I mean by strong nucleophiles? When we're talking about strong nucleophiles, there's 5 categories of strong nucleophiles that we'll see doing this. The first would be our alkoxides, sodium methoxide, ethoxide, whatever the R group is. You can also think about sodium hydroxide in that category. You will sometimes see this done with sodium cyanide, Cn-, and you will also see this done with sodium thiols and thioalkoxides. And if you really think about this, these are some of the same nucleophiles we saw doing SN2 chemistry. So if anything looks familiar, those are all the kinds of things we saw with SN2. Of more interest to me this semester are going to be the reactions with our Grignards and our lithium aluminum hydrides. And we've seen these reagents reacting by nucleophilic acyl substitution with ketones and aldehydes, and specifically reacting with that partially positively charged center of the carbonyl. Let's begin with some simple examples, taking this epoxide, which is known as ethylene oxide. It's also known as oxirain. Thinking about what's going to happen when we put it through its paces with these strong nucleophiles. Now, when we're thinking about reaction with nucleophiles, we need to keep in mind that our nucleophiles are delta minus. So what we want to be looking for is what in our reaction is delta plus. And if you think about the combination of the bond dipoles going towards the oxygen and the ring strain, what you're going to be realizing is that the epoxide carbons are what is delta plus. And so our nucleophiles are going to react with our epoxide. And in this case, since oxirain is symmetrical, we don't need to think any more about that. We just need to think about what our nucleophile is going to do. So our nucleophile is going to attack one end or the other of the epoxide. It does not matter in this case, like I said, because it is not substituted. The epoxide is going to open, so here's the carbon-oxygen bond of the epoxide, the carbon-carbon bond of the epoxide, and this is going to be our new carbon-oxygen bond between the sodium hydroxide that attacked. And then in some step, either with some water that's present, since sodium hydroxide is always dissolved in water, you can think about a proton transfer to give you, again, an antidiol. So, interesting mechanistically, it's another route to an antidiol, but realistically, the reaction that's way more interesting is going to be our Grignard because of the idea that we can add our carbon-carbon bond. So if we think about our Grignard, again, our carbon-magnesium bond is where our arrow is going to start. Open the epoxide, we're going to make O-, and our new bond with our methyl group. Then with our addition of acid, we're going to protonate our alcohol. And this is actually a really cute synthetic procedure because you've made a carbon-carbon bond, but you've also made this molecule bigger by 2 carbons. So you had 1 carbon in your Grignard, and you had carbons A and B in your epoxide, and so 1AB, we've turned a 1 carbon species into a 3 carbon species because our epoxide brought in 2. So that's kind of interesting. If you understand a Grignard, you'll always know what to do with lithium aluminum hydride. Keep in mind that LAH is just a way to package in H-. Again, you can attack either side of the epoxide because in this case it is symmetrical, making the alkoxide anion, and we've added an H instead of a methyl. And then the acid in the last step. Sorry, having a little bit of trouble with it rearranging on me. is going to give us the alcohol. So this is pretty straightforward. The nucleophile is going to attack and give you alcohols. Okay, let's make things more interesting. Let's bring in both some regiochemistry, where is the nucleophile going to attack, and some stereochemistry. So what we're going to see happening when we have substitution here, and keep in mind, we are not in the presence of acid. There's no protonation up here. So since there's no protonation up here, neither of these bonds are weakened. So what we're going to have to do is this nucleophile is going to have to decide, am I going to attack this less sterically hindered part, which is going to be a lot like a secondary center for an SN2, or is it going to go to this more sterically hindered side, which is like a tertiary? And again, because this acts a lot like, if you can keep in mind that this acts a lot like an SN2, you'll actually understand that what you're going to do is you're going to attack the less substituted side because it's less sterically hindered. So what's our product going to be after this attack? Well, let me start by drawing in the things that didn't change. None of these bonds changed. Our Grignard is going to attack from the bottom, adding this new methyl group from the back side. And then your epoxide, when it opened, that stereocenter didn't change. So because this carbon-oxygen bond was up relative to this bond of the epoxide, the wedge out and the wedge dash back, what we see when this ring opens up is that this oxygen is going to be up relative to the other three groups. And what this almost reminds you of is the backside attack, except it's one carbon skipped over because you attacked the opposite carbon of where this guy is. So it's almost like this was your leaving group and he just popped open. You can almost imagine sproing, and there he is up. And then last but not least, your proton transfer step is going to proton. And this will be true with any of our strong nucleophiles. So you should definitely work some practice problems thinking about what you make with lithium aluminum hydride or sodium cyanide or any of those strong nucleophiles. So with what you've got now, you can go ahead and do in-text problem 1316. There's a bunch of them there. And there's some recommended problems after that, 1337, 38, 46, and 47, and of course 17. So hopefully this gives you what you need, and I thank you for your attention.